This next talk is being presented by Breaking Ground. It is Virtualizing Forward Sync by Wang and JUNFENG.
First of all, we would like to thank BSidesLV for providing us the opportunity to present our work. Today, we'll be sharing our journey through our SYNC3 research and teach you how to start your own vehicle security research without having to buy a real car or car parts. We would like to first introduce ourselves.
I'm JUNFENG, and I have been working as a security researcher in the industry for more than 10 years. Most of my time is spent fighting malwares and vulnerabilities. This is my first time to try my hand at the vehicle security. I'm presenting today with my friend Bob. Bob, could you introduce yourself?
Yeah, sure. Hi, I'm Bo. I'm working as a software developer at Google. I'm an active CTF player and a part-time security researcher. This is a rough guideline what we'll be presenting today. We will talk about why we started the project, what is our methodology and current progress, and finally, we'll share what the security community liked the most, some cool bugs we found during our research. Without further ado, let's get started. I'll first introduce the background of our research. First of all, why do we choose SYNC3 as a research target? Well, for one thing, we have one in our lab, but most importantly, Lincoln MKZ is very popular in the autonomous vehicle industry, especially as a test vehicle. A lot of projects are built and tested upon it, such as Baidu's Apollo. The reason for that is there are a lot of third-party distributors who provides Lincoln MKZ as a starter kit for autonomous vehicle development, for example, autonomous stuff. The second reason is that we can easily obtain the full infotainment images since you can just download it online and there's no need to do hardware for on-soldering chips, extracting flashes, etc. Last but not least, nobody seems to have done a public comprehensive research on the SYNC3 platform, and we would like to get a head start on it. Now you may want to ask, what is this thing we're talking about? In Ford's own words, Ford Sync is a factory-installed integrated vehicle communication entertainment system that allows users to make hand-free telephone calls, control music, and perform other functions with the use of voice commands. The first two generations runs on the Windows Embedded Automotive operating system designed by Microsoft, while the third generation currently runs on the QNX operating system from BlackBerry Limited. The most current generation SYNC4, which appeared after our research started, our Lincoln MKZ runs SYNC3, which is the target platform we'll be focusing for our research. Now you may wonder, if we already have a vehicle, why do we even bother with virtualizing it rather than just working on the original vehicle? Well, there are many complicated details. For starters, we do not want to break our test vehicle nor taking it apart. But for our research to go smoothly, we would like to get access to a rooted SYNC3 infotainment. Thus, we tried some options we found online. The first thing we tried is searching if anyone already have rooted an existing SYNC3. Luckily for us, we did actually find someone doing it, and they even posted a root password on the forum. The only caveat for us to get a specific Ethernet dongle they mentioned in the forum, connect to the vehicle, and SH with the root password. Easy, right? Well, not quite. So what went wrong? Ford disabled the USB dongle, the DevC serial USB, after actually finding the initial post. If there's only some way we can get a root shell in the system, well, if we can't break the vehicle, then why not try running it on dev boards? We considered and tried many alternative solutions. The first alternative solution we consider is an easy setup dev board with the closest hardware spec and features, which is the DRA74X EVM. It costs about like $1,500, and nobody's willing to afford that. A cheaper alternative we found is by extracting information from the config in the download image, which is the OMAP5430 ES2 EVM. It's inferred from the environment variables, which we'll talk more about it later, and it costs about like $140. Okay, but can we do better? Yes, the ultimate BeagleBone Black is to the rescue. If you're not familiar with the BeagleBone Black, the BeagleBone Black is a simple dev board similar to a Raspberry Pi, and it officially supports by QNX 6.5.0 SP1 and QNX 6.6 with network driver available. It costs us about $50. Well, it's better, but it has OMAP 3 support rather than OMAP 5, and is limited by the hardware performance, i.e. you have no Bluetooth and it's not scalable for fuzzing, and we still need to pay. So the ideal infotainment research platform we're looking here is a privileged and easily debuggable environment, has individual components we can run observed behavior, such as we can run the individual Bluetooth stack, and it's cheap. Ideally, we want no cost at all. And it's also fuzzable and not restricted by hardware. Solution for us is building an emulator for SYNC3 and virtualize it, which is the focus of our talk. So now we'll introduce you to QEMU Linaro. QEMU Linaro is a branch of the QEMU. The problem with that is it only has QNX 6.5 BSP available and has no network driver and is end of life, so there's no support added anywhere. But the pros of that is that it's really convenient, it has no cost, and it's very scalable, and there's previous work that's already been running QNX on the Linaro, which is done by Malware Labs. So this is what we choose to focus our research on. Now I'll be talking about how to actually prepare the images. So where to actually get the upgrade images? Well, there are like multiple ways you could do that. First thing, you could just get it on the official site. In order to do that, you need a valid VIN number, which is not an issue, as you can easily get one from any dealer website. The second thing you could do is like getting the image from like Fort Modeler enthusiast forums, like the Mustang forum, for example. The structure of the upgrade images is as follows. Most of them are actually navigation information except the ones in the red. And when you extract it, the structure in there contains one MLO, which is the second stage, bootloader, a view boot, the QNX IFS, which is the QNX OS image, the apps.tar.gz, which is the SYNC3 apps, and the version.der for signature file. We'll talk about what these are in the next few slides. So for the version.der, it actually is the signature of the file. It's based on SHA-256 and signed by Ford and verified by the AppSum application. The QNX IFS is actually the OS image of QNX. In order to extract files from it, we need to use the dump IFS from QNX SDP. The version 6.5 is buggy, but the version 6.6 works. There's also the open source version on GitHub, which we posted a link above. And when you also need to decompile the boot script, which is in the procboot.script. This shows you what's initially booting. And with dump IFS, this is easy. You can just dump it to std out. Or if you really want to know how to actually parse the .script binary, here's the source to that. So the useful info in the this is the useful info from the boot script, and as you can see, it's mounting several partitions into dedicated locations, and it's running some of the scripts. So we modified and was adding stuff for the IFS. We'll show why we did this later. Basically, we're following Malware Labs work, which we do make NAND and then do for making the images, and NAND ECC for doing the signature. And 0x0 is start address and 0xE800 is the end address, so you might actually need to adjust the end address accordingly for the signatures. The caveat in here is that we need to modify the image build file to include SYNC3 specific things. This is mainly why we do modification on the IFS, such as like libc libraries, for example. Because the original BSP came in for QEMU Linaro is in 6.5, and the SYNC3 system for our Lincoln MKZ is based on 6.6, so we need to add the corresponding libraries in there. We also need to modify build file to include SYNC3 startup dependencies instead of directories, mount image-specific folders, as you see in the boot script. So we made a couple of tool modifications. The original layout specified in the make NAND does not actually provide enough space for us to fit the modified IFS. So we modified the script to increase available IFS size and output the image size load instead of using the default size. So now to the apps archive. Apps.tar.gz actually only contains apps.img. The format of that is QNX6. It's mountable on Linux, but read-only. As you can see here, apps.img is actually what's inside the SYNC3 that's different for each vehicle provider. So why are we actually doing this? Even with the expansion of IFS modification, we still cannot actually fit the entire apps.tar.gz. So instead, we create and format a QNX6 partition. We add an additional hard drive to x86-64 QNX VM, which uses fdisk to create all partitions and make QNX 6fs to format them, copy files, and using DD to make an image copy. We also did make image.py and this image using QNX SDP 6.6. So the entire apps.img is about 2 gigabytes, and with just the QNX IFS, we are only allowed to upload I think around 500 megabytes or something. I don't remember the exact size, but that's the limit we have on the QEMU flash. So this is the actual layout for the disk partition. There are some helpful tools in there, like SOCAT and NetCat, which you can use for network tools, and there's also like SCP for secure copy and SH, for example. It's like Dropbear, but yeah. We'll talk about more of these later. So now into booting the image. The first problem we're seeing is the missing of SD card. There's no problem with physical BeagleBone Blackboard as we tried. QEMU Linaro with Linux SGuest has no problem as well, but with QEMU Linaro and QNX 6.5 SGuest, there's no SD card device appears. So what's going on here? So it turns out the problem actually lies in the MCSD driver QNX 6.5. We posted the source code link above, and so you could check in the BSP. Basically, there are three important functions: the MC create thread, which creates the control thread and driver thread, and after that, it also detects the presence of the SD card and start the identification process if there is one. There's the MC control thread, which handles SD insertion, removal, and ready event. There's the MC driver thread, which handles interrupts. So after that, we turn on the debug logs and to try to figure out what's going on. As you can see in here, the only thing that's different is the ext state. And it says unexpected interrupt in the state, which we'll find out what's actually happening in the next few slides. So from the debug log, we can see that the problem lies in the state transition MC create thread, which fails to start the identification sequence. Here's we show what happens in the real hardware. The MC create thread will first send out a command 5 to reset the SD card, and SD card will respond with a command complete interrupt. After that, MC create thread will switch its state to MC state ident. Now, in the real hardware, the interrupt coming back from the SD controller will have some amount of delays, and the state transition can happen before the command is completed, as you can see on the left-hand side. So now we have a race here. This is what actually happens in the virtual emulator. The command coming from the virtual SD controller and QEMU finishes immediately, and the command complete interrupt is raised immediately. Thus, the state machine of MC create thread does not have enough time to switch the state to MC state ident, but still remain in MC state idle, thus causing the interrupt processing thread confused and throwing the error. So the ideal fix for this would be to introduce a synchronization privilege between the two threads, MC create thread and MC driver thread. However, for our purpose, having the interrupt thread sleep for a while and preempt the task to create thread solves the problem easily. Note that this was highly impossible to actually happen on the hardware due to latencies introduced in the hardware pipeline. After we fixed the error, we're able to successfully boot our emulated SYNC3. The next infrastructure change we make is for debugging. The QNX SDP provides source level debugging, however we do not have the source in this case, so we need to think differently. QNX does not support local debugging, does support local debugging. In order to debug any, does not support local debugging. And in order to debug any apps in the QNX, you need to use the pdebug program, which is the GDB server end. Pdebug supports debugging over TCP IP and serial port. Here are the example of usages, as you can see on the slide. Pdebug's debugging protocol is self-defined, which is not supported by the official GDB. You have to use the custom version of GDB from the QNX SDP, so you can connect to the target with command line like this. And we also noted that the custom GDB version also implements some useful commands such as file download and upload, which comes in handy during the debugging process. So it wasn't long before we encountered the first issue that impeded us from debugging. Well, when the custom version of GDB stops on a breakpoint, it will check the stack frame even though you do not command it to do so. Then if the frame pointer is invalid address, the GDB will complain about it by throwing an exception. More annoyingly, the exception will be sticking around and no further commands can be processed. To get around this issue, we'll apply further dirty patch to change the throw error function call to printf unfiltered. As the patch needs to be done at the machine code level, it's not as straightforward as showing the pseudo C code here, especially since we need to remove the first parameter. But with a little more effort, it can be done. Now with the debugging environment ready, I will hand over my talk to my colleague JUNFENG, who will explain how we set up the communication channel between the host and our guest QNX.
Think about once we have gotten our VM ready, then the next problem pops up. That's how we communicate with the guest. So by default, the VM has a serial port available, which is the only channel for us to communicate with the guest. Like many other embedded systems, The default console is bounded on the serial port. We can execute the commands through the console with the root privilege. And as we mentioned before, we can also do debugging over the serial port. However, it's kind of awkward as we won't be able to interact with the system through the console during the debugging. Serial port is well capable of transmitting binary data if we configure it in the right way. The code here shows you how we can open the serial ports for binary data transmission. The key point here is to set the terminal parameter properly. Not a big deal, right? I'm not going to explain the code line by line here. We do not have enough time for that. If the serial port is capable of transmitting binary data, then tunneling TCP or UDP over the serial port is doable. Then I turned it to Google for help. I did note that Socket can forward a single TCP connection over a serial port, but it does not satisfy us. And on the Stack Overflows, we found an answer saying that PPPD could do the trick. We tried and failed. We also note that V2Ray has a proxy protocol called marked.q, which allows users to route multiple TCP connections over a single reliable street-oriented transport. But unfortunately, its whole framework is written in Golang, which is not supported by QNX as of now. Supporting it is a bit challenging. Finally, we decided to make our own one. The diagram here illustrates how the tunnel works. To forward the TCP over a single serial port, there are just a few events that we need to pay attention to. They are connection, data sending, and connection close. The program on the left side is running on the host. The right one is in the QNX guest. The process encapsulates the TCP event in the message and send them over the serial port. The acknowledgement packet is really important for congestion control, but it's really inefficient to acknowledge every packet. Instead, we can send acknowledgement packets every 200 packets or even more. Here's the message format. We need the first 2 bytes as the magic numbers because we note that in some cases, if we send data to the serial port of the QEMU too fast, the data will somehow be messed up. We need to make sure that we are able to detect those errors. The connect_ID is the unique identities of the connections, and other fields are self-explanatory. The bandwidth of the serial ports is very small, so we don't want to waste too much space on the header. So we keep the message headers as simple as possible. When we deploy the tunnels, the IP table comes in handy as it allows us to forward any TCP connections to a specific port. To do so, we need to enable the IP forward options. Then here's the command that forwards all the TCP packets to a specific IP address to the local host 444446 TCP port. I drew a diagram to get this process across. When an application on the host trying to connect to the applications in the guest, the kernel module of the IP table will intercept the packets and redirect them to the tunnel process server, and then the process server encapsulates the packets by adding a header and send them to the process clients in the guest. So here's the demo of the serial port. We bring out the VM first while waiting for the tunnel to be ready. We check the redirection rules in the IP table, and we also add the static entries in the host files for convenient purpose. Once the tunnel is ready, we're going to log into the guest. Okay, just wait for a few more seconds. Now it's ready. Then we can SSH into the host, and let's check the environment. And then we try to upload the file into the transfer the files to the guest. The speed is kind of pathetic. And then we also trying to download the files from the guest. Also, it's really slow. Then we try to post the file by this curve call. This post would not touch the IOS, the file system. Then you can see the speed is still really slow. Yeah. So to summarize the implementation, the good point of our implementation is that it supports multiple concurrent TCP connections, which means you can access the consoles while you're doing the debugging. It functions completely as expected. The bad points of this implementation is that it's pretty slow, as shown that the speed of the serial port is the bottleneck. Can we improve the implementation? The answer is yes. A little later after we complete the serial port tunnels, we came across a blog from the Alpha Security. They encountered similar problems when they virtualized the iOS system. Then they devised a smart idea. Here's a brief introduction to their solution. They defined a custom system registers at the QEMU layer. Any programs in the guest read or write, the registers will trigger the callback functions, and the callback functions act like the RPC stop. There are some drawbacks of this prototype. First, it lacks signal support, so that the programs in the guest must perform the infinite poolings, which will render significantly high CPU usage. If we let the programs sleep between pooling, that can help, but still had rooms for improvement. Second, the prototype only supports a single TCP connection at all times. That's pretty much like the sockets we mentioned earlier. Third, there are some potential bugs such as writing the swap out memory of the guest from the QEMU layers, which might lead to memory crashing problem. And the prototype also assumes that the definition of the error numbers are the same between the host and the guest, which might not hold true in some cases. We might need to do the translation for the error codes. So after reading Alpha's security post, an idea struck us that we can combine these two channels to create a fusion channel. We can turn the serial port into a signal channels. We can send one byte to the guest to notify the guest programs that we are going to send a data packet. The data channel is based on the QEMU custom register. The packet format is exactly the same as the serial port tunnel. Moreover, for the best performance, we implement the fusion tunnels based on libEVs. Yes, it supports multiple concurrent connections. Besides, we also add the error code translation and fix those minor issues. Some of you might wonder why we don't add a new interrupt for the signal support. That's because we want to keep the channel as universal as possible, because for some systems it's really hard to add the interrupt support. To implement the fusion channel, we first need to define a concurrency register. We cannot just copy and paste the codes from Alpha security prototype, since theirs is for ARM64 and our CPU is different. The patch here is very clear. You need to pay attention to the SS fields. The PL0 write and W allows the programs from the user modes to read and write the register. And then there are the read function and the write function callback. The read functions will simply return the operating system type of the host, and the write function is responsible for dispatching the function calls. Here's an example code for writing and reading the custom registers from the guest system. The QC_get system simply retrieve the operating system type of the host as we mentioned it. Here's the incomplete list of the error code on different operating systems. We can see many error codes vary vary from parent phone to parent phone, and that's why we need translation. Here's our implementations. It's very simple. So we define several two-dimensional tables, so we can convert the error codes by simply consulting the tables. Here's an example of calling from the guest. The code is self-explanatory. We use the QEMU code structure to encapsulate all the parameters that we want to pass to the QEMU layer. The line highlighted here in yellow lock the buffer in the physical memories. Technically, we should also lock the Q code structure, but because it's on the stack of the current active thread, it's highly unlikely to be paged out to the disk. So we decided not to lock it in the physical memories. After the QEMU return, we convert the error number. Another caveat is that the size of the data type may be different between the guest and the host. You have to handle them with care. Okay, another demo. And this demo, let's take a look at what we have achieved. So here, as we can see, we also use the IP table, and then we also add the entries in the host. When the tunnel is ready, we are going to try to log into the guest. Yeah, just wait for a few more seconds. Yeah, it's going to be ready. Okay, it's almost there. Yeah, then let's log in the guest. And the environment is exactly the same as the last one. So let's check the speed. Well, as you can see, the differences, right? Compared to the serial port, the speed is really kind of magnificent. Yeah, we like that, right? So, okay, after so much hard work, finally we come to the most exciting part. We are going to pick the fruit. So when we try our hand at the vehicle, we wanted to root the head unit for researchers. So we spend a little time on the some application, which is the application that is responsible for update or an upgrade, in which we found command injection problems which affect the SYNC3 versions released earlier than April 2018, including the version that was released in April 2018. Successfully exploiting this vulnerability can allow attackers to execute arbitrary commands on the systems with root privilege. To exploit these problems, physical access to the vehicle might be needed. Man-in-the-middle attack can be another hacking avenue, but we have not verified that. Interestingly, reading through first vulnerability process on hack1, it seems any vulnerability that requires physical access or man-in-the-middle attacks are considered out of scope by fraud. So that's really interesting. The vulnerability involves two key functions. The first one is to parse the LSD files such as auto-install.lst. The image here shows how the LSD files look. It's not signed in, and the get version info _fpn functions will call another function to extract the version.dir from the upgrade archive to verify the integrities of the archive. The problem is in the process of extracting the file. Here's the code that extracts the dir files. We can see that it calls the snprint function to construct the command line. And then it calls the execute self commands, which later just call the system functions to execute the command. The archive name is highly but not fully controllable by us. Noticing there's no quote surrounding the parameter. Yes, so that is exactly a command injection problem. When the programs pass the LSD files, if you check the archive names, a long list of those chars are considered malicious. You are not going to be able to use them in the file name. So besides except for the those malicious chunks, there are two more bad chunks that we can use. There are the slash and the backslash. The backslash can be used if you prefer to update through the Wi-Fi instead of the USB thumb disk. The culprit are those two functions named manipulate strings. As their name suggested, they manipulate the strings. Yeah, and any directory part of the archive names will be removed during the part reconstruction. Let's say we craft an archive path like this. The final commands will look like as follows. We can see only the base names is remained. We note that many dangerous chunks are not filtered, like the dollar symbols and the brackets and the back quotes. Moreover, the space is also available, so we don't even need to use any trick like the IFS. To briefly summarize the major constraint, the first one, we can use the slash and backslash, which implies we won't be able to reference any location that are not in the environment variables. And the second limitation is that we can concatenate multiple commands. The appsum's current working directory is not writable. You can let the tar programs to you can let the tar programs extract files to the current working directories, and many of those environment variables are not usable because they do not end with slash. If there's no slash at the end, we can construct a valid path. Take the temp directory environment variable as an example. If we put the file names right after the variable, then it produces a string like this, which is not what we want. All the constraints can be circumvented. Here are our solutions. The first one is really straightforward. Pdebug is a built-in program on SYNC3. We can use it as a backdoor as well. Here we let it listen on 8,000 TCP port. Then we can connect our GDB clients to the port and gain all accesses. The second approach is more intriguing. We add the malicious scripts to the upgrade archive. Then we let the tar programs release our scripts to a writable position first and execute the script in the next round. The programs will execute these two commands. We use the environment variables that ends with the slash. That's really helpful. Thank you. Thank you to SYNC3. For the refactor, the appsums and the vulnerabilities has been fixed. Once only God knows whether or not they have ever been aware of this issue, and the upgrade link has also been changed from HTTP to HTTPS. Then we move to the next target, the Bluetooth stack of SYNC3, which is based on INVS, and the SYNC3 support a bunch of profiles, including the phone book, access point, etc. If you happen to have a card, you can try to scan all the profiles with the command here. SYNC3 Bluetooth stack support most commands, most common PSM as well, with just one exception, that the BNAP is not enabled by default. The BT stack is the Bluetooth stack of the SYNC3, which heavily use the BSS segments instead of HIT. As a result, it's really hard to distinguish the boundaries of objects. And it also poses difficulty to fuzzing, because in most cases, read or write out boundaries in the BSS sections can be perceived. The BT stack is event-driven, and there are a lot of callback functions, which make it difficult to do the static reverse engineering of the program. However, the BT stack comes with abundant debugging logs, and it's really easy to enable all of them. They are really helpful to us. The diagram here shows how the Bluetooth stack works. The BT stack is Bluetooth driver of the host. We need a Bluetooth driver to complete the puzzle. So according to our analysis, the BT stack will communicate with the Bluetooth device directories if the serial BT5 present on the system. How to create a fake serial port, because we do not have a physical one, then we need to create a fake one. Well, we can write a QNX resource managers programs, or just utilize the socket program. Using a command like this one can forward the TTYP0 to 80 TCP port. It's really handy, right? After creating the pseudo serial port, we hook the open functions in the BT stack program and redirect the path of the serial port to the pseudo TTTY. That's not enough, actually. To simulate the serial port, we also need to hook the device control function. The purpose of this is that when some programs are trying to detect if the serial port is ready, we need to let them know that we are ready for data transmission. So well, we are almost there. By reverse engineering, we figure out that the BT stack would wait for an uncanny message. We need to feed it the message. Once again, we hook the receive message functions and feed the message. Here's the definitions of the message structure. Honestly, I'm not 100% sure about the purpose of all those members of the structure. I just know that it can kick off the BT stack. The BT the Bluetooth. Okay. As we know, we need host controllers. We can port the Bluetooth emulator, or even use the physical controllers on the Linux host. But eventually, we decided to write a simple host controller. The Bluetooth HSI protocol is relatively simple. In our case, we just need to pay attention to a handful of events. Here's a snapshot. Here's a snapshot. If you look close to the source and the destinations, you can see that the HSI event is the response to the HSI command. We need to replay the HSI event only. So you might wonder why replaying. Well, because we don't want to craft those packets. That's kind of tedious and painstaking. To replay, you just need to pass the BT Snoop package file and correlate the HSI commands with the HSI events. Please don't forget to update the HSI handle when replaying the package. It's fine if you want to replay the HCL data package, but perhaps you need to do a little more parsing. Wait, we still need to tackle one more issues before bringing up the BT stack of the SYNC3. When the program tries to create a shared memory object under the temp directories, it will fail because the file system just doesn't implement that function. So, however, luckily we are able to create folders in the FAT32 partitions. So again, it's really easy to redirect the access with hooking again. So here's the code. We hook the SHM open function, and then if like the path starts with the temp, then we simply redirect it to our writable position. Okay, here's the demo. Shows how we bring out the Bluetooth stack. As we can see, we have 4 pens here. The top left pens was running the virtual machines, and then we execute the command to launch the ss_launch process in the top right pens, and which could bring out the service that the bit that depends on. After that, we start the virtual Bluetooth host controllers, which named the VHCI. And after the virtual host controller got ready, so then we bring out the Bluetooth stack, and we can see the virtual host controllers was rapidly outputting the logs of HCI packets, which means the BT stack was interacting with the virtual host controller. Yeah, we make it finally. So we found 2 vulnerabilities in the BT stack. One had been avoided. Yeah, the other one is still waiting for processing. We also found some other harmless read-out-bound bugs, which we have not reported as they made no harms whatsoever. And I don't think Ford will give a shit. We also reached out to Ford 1 month ago for permission to disclose the details. We haven't received any response from Ford as of now. So, and the both tickets are still open. So unfortunately, we are not able to share the details of these bugs here this time. Oh, that's kind of the pity. And here's the final thought. Yeah, definitely having a vehicle for research would be really helpful, but it's not much. We found and verified all the problems with only the virtual environment. There are still many venues we can explore. Please feel free to DM us at Twitter if you want to discuss, or if you have any brilliant idea or that you want to share with us. All suggestions are welcomed. Yeah. Thank you, and please let us know if you have any questions. Yeah, that's all. Thank you.
So we were chatting beforehand before we got to the QA, and I heard you have some updates for us.
Yeah, thank you everyone for listening. So yes, we would like to rectify our mistake in the presentation. First, the vulnerabilities in the app sums was actually fixed in the late 2015. For improve the character filter, which only allowed the whitelisted characters. So as a result, you won't be able to inject the cell command anymore. But according to my analysis, it seems the patch was not thorough. I'm still working on the POC to see if the patch could be bypassed. Anyway, the problems has been thoroughly patched by Ford's inventories since they changed it to the lib archive. We made the mistakes because we only used the command lines as the vulnerability indicator when we trying to determine the affected versions. We apologize for the mistake, and hopefully that these clarifications could, yeah.
Great. Well, I mean, mistakes happen. I'm monitoring the Discord, so if you have questions in the Discord, go ahead and I can ask the speakers. I've got some questions for them because I really like the content and the material, so I'm gonna ask them. So, in your opinion, what was what was the hardest part, or maybe like what surprised you the most when you started doing this research? Both of you.
I think for me, the most surprising thing is that it actually works. Because like originally we didn't actually expect this to work. I mean, like it's easy to like hack a car if you have a car, right? Like, or if you have like a workbench, but like just having like a simulator is pretty hard to imagine, I guess. And also like QNX isn't like a normal operating system you use every day, so it's like the infrastructure side on that isn't really great for support. So like we hacked a bunch of things, and yeah, we got it to work finally. That's like most surprising for me.
Nice.
From my side, I think the most difficult thing is that you when we started the project, we just could not foresee how many obstacles lying ahead. So at the time, at some points in the middle, we just had no idea whether this is doable. So as we were facing so many problems, and we just had no idea how much effort required to make it work. So that's the most frustrating challenges we face during the research. And regarding another things, like you do not have a reference point, if like because we do not have a vehicle, and then if like you have vehicle, you have reference points, you could quickly do the debugging on the vehicle, some sort of those things, and then you know what kind of thing you are missing. But because we do not have that luxury, then what we need to do is we need to do a lot of the reverse engineering, and it requires a lot of those skills in the reverse engineering. You have to do the static reverse engineering to figure out how to make the thing work. I think that's the most difficult. Yeah, the most difficult thing.
Yeah, I think I just want to add a couple of sentences on that. So like there's like a lot of like state machines and like static lib compilations in there. So if you have like a dynamic infrastructure like a car, then you could easily verify if like your reverse engineering results was correct. But if you don't have that, then like basically you have to guess, or like just statically reverse engineering the whole thing, which is like a huge complication for us as well.
Yeah, I can completely understand. You both mentioned that you've been working on this for a little while. How long have you guys been working on this for?
I think since we started the project, it has been almost 2 years. Almost 2 years. But it's not a continuous work. At some of the middle point, as I mentioned, that we do not have the confidence that this was going to gonna work. So we somehow just put it aside and turn to other work, and then later we pick it up again and just kind of those process. Yeah, start and go, and something like that. Some sort of that kind of thing.
How did Ford respond to the vulnerabilities?
So for the app-thumb, we realized that basically it has been fixed in the latest version. It's kind of the thorough patch. So according to their disclosure process on HackOne, they said this kind of vulnerability requires physical access or man-in-the-middle attack. They consider them out of scope. So then, even though if it affects the latest versions, I think they will not accept the report there. And then another for the other vulnerability I report for the first one, the Bluetooth one. Then it took them about 3 months to give a response, and they said, okay, we confirm the vulnerability, and we are going to give you a bounty. And for the then for the second one, we report them, and they have not give any response. And that's kind of interesting. And we also reached out to them for permission to share the technical details 1 month ago. So that, as of now, we have not received any response from them.
Great. It is really interesting research. Where can we follow you to keep following this?
Yeah, we as you can see in the presentation, we there are Twitter, so you can follow us. Maybe we are going to publish the slides a little later. Yeah.
What's your Twitter handles?
Yeah, Twitter handle is Blue Last. How could I just simply type here? I think in the on the last slide of our presentations, you can find our Twitter name.
Great.
Yeah, feel free to DM us for any questions you have.
Yeah.
Well, great. Thank you so much for presenting at BSides Las Vegas. I really enjoyed this talk, and thanks again.
Thank you for giving us the opportunity.
Yeah. Thank you. Yeah.